I would like to speak about the growth of continental crust. And I put here a diagram where we can see we can see the number of papers published each year about the genesis of the archaean crust. Archaean are terrains older than 2.5 million years. So we can see that the scientific community paid more and more attention to this topic of the genesis of continental crust. If we look at the continental crust, here is a typical outcrop of continental crust in Karelia, in Finnish Karelia. And we can see that we have three kinds of rocks. We have a gneissic basement. So the gneissic basement is in yellow here. We have greenstone belt in green and late granite in red. So during this talk, I will speak only about the basement. If we look at this basement, so here is an example of this basement. And when plotted in a diagram with feldspar, anorthite, albite, and orthoclase, we can see that this rock plot all together. There is more than 1,300 points in this diagram. And all the data plot in the tonalite, trondhjemite, and granodiorite field. So this is the reason why they are called TTG. In fact, these rocks are very sodic. In a potassium, sodium, calcium diagram, they plot very close to the sodium apex of the triangle. And from this point of view, they differ from the modern continental crust. When I say modern, I say younger than 2.5 billion years. And this modern continental crust is not so sodic, but in fact, more potassic. There is the same difference about rare earths. Typically, the archaean crust has very strong fractionated rare earth patterns and with a low heavy rare earth content. And when compared to the modern crust, where the heavy rare earths on the right of the diagram are not so low. The normalized content is greater than 10, when it is obviously less than 10 and very often less than 5 for archaean rocks. So there is a big difference between these rocks. And geochemical calculations lead to this classical model. That is that, of course, these rocks are generated by melting of a basalt. So there is a first stage of genesis by melting of the mantle to give rise to a basalt. This basalt subsequently melt with hornblende and garnet-bearing residue. They give tonalitic magma, and finally, some fractional crystallization give rise to the whole TTG suite. The important point is that in order to generate these rocks, we need to melt a basalt. And the classical environment, imagine for this kind of rock, is some kind of a subduction where the basalt are generated in a ridge and they are molten in a subduction zone, just like we can see here, by melting of the subducted slab. So this is the general idea we had about the genesis of the continental crust. It is generated by melting of oceanic basalt, of what we call MORB for mid-ocean ridge basalt. In fact, this is not so clear. For instance, here, if we plot a lot of, there is a lot of elements, and they are plotted against the MORB composition. So in green, we have the composition of a MORB. Here, we have the composition of the archaean TTG, an average archaean TTG. And here, we have the result of modeling. This is a mathematical modeling of melting. So that means that when we melt this basalt in green, we obtain the blue line, the blue pattern. And in fact, we can see that there is a big problem for some elements, just like rubidium, barium, and thorium. So it seems that for most of the elements, models can account for TTG composition, but this is not the case for a group of elements just like barium, thorium, uranium, barium, and so on. So we can try another possibility. It's possible to model the melting of another kind of basalt. This is a basalt from a hotspot, from some kind of oceanic plateau, for instance. So this basalt is richer in some elements. And if we compare, of course, with TTG, the result of modeling is in excellent agreement with the data. So this is the first point. It seems that here, if we look at modeling, it seems that melting of a morb of oceanic basalt cannot account for the composition of archaean TTG, and the best source should be some oceanic plateau basalt. Okay, we would say this is only mathematical modeling. So we can try another approach, and this approach consists in melting, experimentally melting basalts in order to see what is the composition of the resulting magma. So here is a device we use in Clermont-Ferrand, and if we melt basalt, we will obtain rocks with TTG composition that are sodic in composition and with strongly fractionated patterns with low heavy rare earth contents. So when we look at all the experiments that were done until today, we can see that two kinds of sources were experimentally molten. If we plot in a potassium versus silica diagram, we can see that some of the sources of the basalt used for experimental melting have low potassium content. They correspond to different kinds of mid-ocean rich basalts. And another group is richer in potassium, and they correspond to, for instance, here there is Galapagos, Carnegie Ridge, and so on. They correspond to hotspot or to oceanic plateau basalt. So in the literature, we can find the result of melting of two kinds of different basalts. So now we can plot in the same diagram the composition of archaean TTG. So there is a nice widespread of data, the spread in the wall diagram. And now if we look at the composition of magma produced by melting of the, let us say, potassium-poor basalt, we will obtain the green triangles here. And obviously, this cannot account for the whole distribution of archaean TTG. If now we melt the potassium-rich basalt, the potassium-rich source, of course, we have the blue triangle, and they can account for the whole distribution of archaean TTG. So here also the conclusion is that melting of a morb is not a suitable process in order to account for the composition, for the whole composition of archaean TTG. Here is another diagram. In course of time, here we have the lutetium-hafnium ratio, so isotopic ratio. Here, the yellow dots represent the composition of zircon, and the green line is the chondrite composition, so more or less the composition of this zircon from TTG is consistent with the chondritic composition. And here, in blue, is the composition of morb. So once again, the composition of this archaean TTG is not consistent with the source as a depleted mantle that is the source of morb, of this mid-oceanic rich basalt. So this is the first point. The second point is that when we look at different models of growth of continental crust. So here is an expected amount of continental crust against the edge. And all these models, of course, show that the continental growth was extremely rapid, efficient during the archaean, so in this part of the diagram, and less efficient after. But all these models, these curves, show some quite regular increase of crystal growth. So the curves are, let us say, more or less flat and regular. And in fact, when we look at the continental growth using other data, for instance, here, this histogram is based on Samion neodymium model ages, we can see that the continental growth was not so regular. There are some peaks in crust production, and for instance here at 3.8, 2.7, 1.8, and so on. So looking at this, it seems that there were episodes of intense crystal growth at some moment of the history of the continental crust. If we look at zircon data, these data are from Carnegie and Haster, and the next one are from GITRO. We can find, again, episodic growth with some very important peak of crystal growth at 1.8, 2.7, 3.4, 3.8, and so on. So it seems that the crystal growth was something episodic. And this is not consistent with the subduction process. Subduction is very regular processes that should produce quite regularly continental crust. And what we observe is not a regular production, but episodic production of continental crust. This is not consistent with a subduction or classical subduction process. So, okay. One of the models proposed by Condi and Sterne-Hoffmann several years ago, in order to account for this, is a model of cold avalanche. So they consider a place where a cold oceanic crust, so in green here, is being subducted, and the cold material accumulate at the 600 kilometers boundary here, at this interface, and it accumulates more and more, and finally, after some time of several hundred million years, this accumulation breaks the interface and sinks into the lower mantle. So this is what they call a cold avalanche here. And of course, if cold material sinks into the mantle, some part of the hot mantle will rise, and of course, this will generate mantle plumes, hot mantle plumes, just like this. And of course, these plumes will induce some magmatism at the surface, and this magmatism today is magmatism of oceanic plateau or traps. So the idea is this idea. So you accumulate cold material at this interface, and from time to time, the time span is of several hundred million years, there is this cold avalanche and the ascent of hot plumes. This is not something only theoretic. If we look, for instance, here at seismic tomography, here this is in the Tonga area, we can see in blue cold material, that is a subducted material, in red something warmer, and we can see, I have no pointer, I don't know how to use it. We have accumulation of material near the 600 kilometers interface, and it seems here that some cold material begin to sink into the lower mantle. The same here in Japan, where we can see accumulation of cold material and sinking to the deep mantle. And of course, so I come back now to the model of ascending mantle plumes. They give rise to what we know as oceanic plateau in green here, emplaced on the oceanic crust, and traps emplaced on continental sky like Siberian or Deccan traps here. So maybe we must research the origin of archaean TTG in this kind of environment. And very nice, if you look at the oceanic plateau, they can contain felsic rocks, but the amount of felsic rocks is very low, less than 5%. And if we take into account a very special situation, just like here in Iceland, where we have a ridge that interacts with the mantle plume, the amount of felsic rocks never exceeds 10%. So, okay, it's possible to have felsic rocks in oceanic plateau, but the process is not very efficient. Moreover, if we look at, for instance, here, this is a TTG rare earth pattern. If we look at the composition of felsic rocks produced in oceanic plateau, here we have Iceland, Hawaii, Kerguelen. Obviously, they are strongly different from archaean TTG. The same if we take into account more elements. I think I have it, okay? So we have more elements, but the result is the same. The pattern of felsic rocks that we find in oceanic plateau is drastically different from the composition of archaean TTG. So the conclusion is that today, in oceanic plateau, when we have felsic rocks, they are absolutely different from archaean TTG. So what is the possible solution? There is what I would like to call a modern analog of an interesting process. And this happens here in Ecuador, so in South America, in the northern part of South America. And in this place, we have the South American plate with Colombia, Ecuador, and Peru. We have the Galapagos Ridge that separates the Coco Plate and the Nazca Plate. And on the Nazca Plate, we have a hotspot that gives rise to the Galapagos Island. And there is an oceanic plateau. There are several oceanic plateaux, but one that will interest us, that is the Carnegie Ridge. The Carnegie Ridge corresponds to the basalt generated at the Galapagos hotspot. So this is an oceanic plateau, and this oceanic plateau enters in subduction beneath South America. There is a lot of volcanoes. Each point represents a volcano here. And if we look at the position of the ridge, of the Carnegie Ridge at depth under the South American continent, we can see that most of the volcanoes are located above the place where the Carnegie Ridge is being subducted. So, okay, the same. And there is a lot of volcanoes during a Quaternary era. There are 55 volcanoes above the place where the Carnegie Ridge is being subducted. So there is a lot of volcanoes. This is an abnormal amount of volcanoes in this area. These volcanoes are very active. Here are two examples, Tungurahua and Pichincha. And now, if we look at a map of the whole South America, we have several volcanic zones, the North Volcanic Zone, Central Volcanic Zone, South Volcanic Zone, and Austral Volcanic Zone. And we can try to plot here the amount of volcanoes reported to a length of the subduction that is correspond to 100 kilometers. And what clearly appears is that in Ecuador, above the place where the Carnegie Ridge is subducted, the amount of volcanic edifices is clearly greater than everywhere, more to the north or more to the south. So the conclusion for this could be that, of course, the amount of active volcanoes increase above the subduction of oceanic plateaux. So there are more volcanic edifices. But if we look now, not at the whole volcanoes, but at individual volcanoes, we can see that above the place where the ridge is subducted, the production of magma is about 0.4 to 0.5 cubic kilometer each 1,000 years. While more to the north and more to the south, all along the subduction under of the Pacific under South America, the production is, of the other volcanoes is less, 0.05 to 0.2 cubic kilometer per 1,000 years. So, the conclusion of this, what information provides this analog, is that when an oceanic plateau is subducted, it results in an increase of the amount of volcanic edifices. And in addition, each of these edifices, have a very high magmatic productivity. So, if we combine both, this result, we can conclude that the subduction of an oceanic plateau results in an important augmentation of the volcanic productivity. There is a greater amount of magma generated. So, okay. So we can jump from this analog to the past and consider that the TTG, the archaean TTG, have been generated by melting of oceanic plateau and maybe in subduction environment. If we consider this, we consider that we can account for this difference we have seen, and we can also account for the episodicity of the process. The episodicity is not linked to the subduction, but the episodicity is linked to the genesis of the oceanic plateau. The process of cold avalanche will induce an episodic process of oceanic plateau genesis, and when this plateau will enter in subduction, they will melt and give TTG. So this can account for the episodicity of production of TTG. So, now what could have been the implication? Of course, this process will result in an increase of magmatism. Increase of magmatism in the genesis of oceanic plateau, but also magmatism due to the subduction of this oceanic plateau. So, one of the effects could be as Axel showed, to an increase of the hydrothermal activity, which can correspond to some environment favorable for some kinds of life. And here is not South Africa, but it's Australia. And you can see a lot of chert. All the brown rocks are chert here in Australia. So it's a strong development of chert. But also, they can modify the environment in surface. For instance, here, if we look at one eruption in 1982 in Mexico, in El Chichon, this volcano ejected in atmosphere a lot of ashes. And if we look at the development of the ashes, they turn all around the world. And, of course, they induce a decrease of the transmitted solar radiation at the surface of the Earth, and they make a very strong peak of this result in a colder weather. If we look now at another volcano, here is a Pinatubo in the Philippines. If we look now at the amount of aerosols H2SO4 in the atmosphere, so before the eruption, immediately after the eruption, so there is a lot of aerosol in the atmosphere all around the world. Now, 3 months after the eruption, and we can see that 9 months after the eruption, a lot of aerosol remains in the atmosphere. And the effect of this eruption was also sensible. We can see it on the light from the sun arriving to the surface of the Earth. Last point, this kind of hotspot activity, if it arrives, for instance, here in a supervolcano, just like Yellowstone here, so it can provide special environments, but also a very strong eruption. Here, this is a result of a super eruption 2 million years ago, and this eruption covers, the ashes covers a very large surface, and between 20 and 60% of the ozone layer has been destroyed by this eruption. Now, and I will finish with this slide. Here are the Siberian traps. So they cover a very wide area. And these traps, the emplacement of this trap at the boundary between Permian and Triassic period lead to the extinction of 90% of the marine species. So this, what I would like to say is that all this volcanic activity, this peak of volcanic activity, should add very strong consequences on the environment at the surface of the Earth.